Alrighty, good afternoon, lads and ladies. Today, we are going to talk a little bit more about integration and try to wrap up the stuff we've been doing by showing you one or two little applications. The start of Calc 2, we will be kind of building on these applications and going a lot further. I'm going to close the door to my office and then get started. Okay. So I want to give you guys more practice working with the substitution rule, especially with definite integrals, because I know we need that. And at the same time, I'd like to move forwards a little bit and discuss one or two final concepts with you before the end of the term. Excuse me. Okay, here we go. So of course, this is Calc 1, Section 4. It is a lecture. And today is the 30th of November. So, a few things. First, I want to talk a little bit about this study guide and homework assignment that's up now. So, quick little announcement. I'll show you here. Clearing out all the extension requests. Looks like I got a few more. So the last assignment that you'll see in WebAssign is the study guide 3, and it's longer than most study guides. Most of the study guides I've published had like 10 problems, and this has 16 problems because it's not just a study guide, it also is your last homework. So I've folded the last homework assignment in with exam 3 study guide because I don't want to overload you guys with stuff to do. I don't want to give you, 2 fresh assignments this week and a test on Friday. I feel like that's way too much. So this is your homework, and it is the study guide for exam 3. So think of it as homework 13 and also study guide 3. What that means is you do need to write solutions to these and scan those solutions, submit them in Canvas under the assignment titled Study Guide 3. So just like you did for Study Guides 1 and 2, make sure that the solutions to Study Guide 3 land there. But some of these problems are new problems. Some of these problems are old problems. So I want to talk to you a little bit about the newer problems, namely the sort of areas between curves problems like numbers 7 and 8, 5, 6, 7, and 8. That's the last new bit of content. So Study Guide 3 is a mixture of old and new problems. The new problems are from section 6.1 on areas between curves, which we'll cover today. It's a very quick section. You won't have a hard time with it. Still 25 points for the study guide. No, same as always. Still 25 points for the study guide. Yep. The point value associated with the length of the assignment is factored into the homework grade in WebAssign. So the point value that each homework assignment is worth in WebAssign corresponds to the number of problems that are in there. So both of those things are figured in, but when it comes to the study guide grade, it's just out of 25 points for completeness, not for correctness, on the work you submit in Canvas. So to get credit for the study guide, you got to scan and submit the work in Canvas. And as long as there's a good faith effort there on each of those problems, then you'll get full credit. There is no separate study guide for the final. To study for the final, I recommend looking over the old exams, looking over the old study guides. Generally, what I would say is go into the textbook and make sure you can solve all the problems from all the sections that we've covered. That isn't to say between now and the final, I expect you to go in and solve every single problem, but you should go through the textbook and kind of make a survey. Which sections were hard for you? Which sections were easy for you? And in the sections that were hard for you, go in and make sure you solve at least 3 or 4 problems per section. Final exam is going to be a little bit longer than a regular exam. I would expect around 20 questions. And you'll have 2 hours to complete it. No, it's not a department final. So the last class in the calc sequence to have a department final is MAC2311.005. Everything after that, faculty members write their own finals. Can we get a practice final? No, there's no practice final or anything like that. It's not a uniform thing across the department. So every semester for every class, professors are supposed to write a fresh final exam for their class. Some professors break those rules and reuse final exams, but I sure as shit do not do that. So every semester I'll write a fresh final. I don't have a practice final for you, but like I said, go through the problems from the old midterms, go through the problems from the study guides and the homework, and you'll be in good shape. If you're looking for extra problems though, I think the best place for you to study is to go to the chapter review in the textbook and make sure you can solve these problems. And you may notice if you look at the chapter review, there is a correlation between the true, false, and multiple choice type problems that you'll find here and the true, false, multiple choice type problems that you will find in my midterms. So in preparation for the final, I would go back and look at chapters 1 through 5 and make sure you can do these review problems. Okay. So today, we're going to cover section 6.1, which is on areas between curves. So first, I want to give you a basic idea of the picture here. I have some coordinate axes, x, and then maybe I have 2 functions, right? Maybe one looking a little bit like this, which I'll call f, and what color is this? Is this also purple? Blue. Let me do a slightly stronger color though. Let's do it like this. G, red. Oh. And I'd like to find the area between them, say from x equals a to x equals b. Now, if I was to come in here and integrate from a to b, just the function f of x, the blue function, that would give me this area. And if I were to come in here and integrate from a to b, the red function f of x, that would give me this area. So the question is, how do I get at the stuff I want, the area between those 2 curves? The answer is it really depends on where you're looking. So this intersection point is special. I'm going to mark that as C. The area between the 2 curves is this area here, which is just blue, and this area here, which is just red. If I want to get the area, let's just look from A to C. So the area between f of x and g of x for a less than or equal to x less than or equal to c Well, imagine I take this blue area, all the area that's shaded blue, and I subtracted the area that's shaded red. It's all this blue area minus the red area. Would you agree? I take everything here that is blue, that's this whole thing, and I subtract out the stuff that is red, that's this stuff. So this would be the integral from a to c of, well, I'll write it like this, f of x dx, that's the blue, minus the integral from a to c of g of x dx, that's the red. But I can put this together into one integral, that's the integral from a to c of f of x minus g of x. So if I'm looking just from a to c, just at this stuff, if I want the area that's between the red and the blue, I take the area that comes from the blue function and I subtract the area that comes from the red function. That's going to be all of this, right? Like all of this, minus the stuff that's just under the red. And you can put that together into a single integral like this. Blue is f, yeah. Red is g. Okay. And now if I want the area between, same thing, between f of x, which is blue, and g of x, which is red, from c to b, here, what do I need to do? Well, here's all this red area here. I just want the stuff that's between them here. So if I take all this red area and I subtract out this blue area, because now the red area is larger. So I take this and I subtract out the blue, that will leave me with the area that's between them. And what is that? Well, all the red area is the integral from c to b of g of x dx. And then all the blue area is the integral from c to b of f of x dx. So this is the same. You combine it into one integral, integral c to b g of x minus f of x dx. So what you see is that to get the area on any interval that's between two functions, you subtract the upper function minus the lower function, and then you integrate. Right? So from a to c, if I want to find the area that's between f and g, then I would integrate f minus g from a to c. And similarly, from c to b, if I want to find the area that's between the red and the blue, I would integrate the red function minus the blue function, g minus f. Your book has another way of writing this. They say you take the absolute value of f minus g and integrate that. But in practice, the way you do that is by splitting it up into these cases here. So this is the easier way to think about it. So this is our jumping off point. Let's look at an explicit example. It would be nice. Let's see if we had something that required a little substitution, but maybe we'll build up to that. Let's look at a simpler example first. right? Find the area between f of x equals x squared and g of x equals x cubed from x equals 0 to x equals 1. So I'm going to draw this zoomed way in. X squared, if I zoom in, it's going to look something like this. And x cubed, they hit each other at the point 1, 1. And x cubed actually sits below x squared. And then he has this like S shape, Right? They touch at 0, 0 here, the origin, and they touch up here at 1, 1. So the area I'm looking for is the area between these two curves. And I can think of that as the area under the blue minus the area under the red. So if we follow the formula here, the area I want is the integral from 0 to 1 of the upper function minus the lower function. That's really the way to think of it. And the upper function here between 0 and 1 is f of x, or x squared. And the lower function, the red function, is x cubed. Right, the blue here is f of x equals x squared. The red here is g of x equals x cubed. So upper minus lower. That's it. And if they cross, you have to split it up, right? If they cross, then the upper and lower switch, or have the potential to switch. This is not a tricky integral. You find your antiderivative using the power rule. An antiderivative for x squared is x cubed over 3. An antiderivative for x cubed is x to the 4 over 4. And we evaluate this from 0 to 1. That would be 1 cubed over 3 minus 1 to the 4 over 4. And then we subtract what we get when we plug in our lower bound. That's 0 cubed over 3 minus 0 to the 4 over 4. And this is just 1/3 minus 1/4. And you can write those both as ratios over 12. This is 4 over 12 minus 3 over 12 is 1 over 12. Not so bad, right? Questions on this? The good news is that the recipe upper minus lower always works, regardless of whether both are above the x-axis, both are below the x-axis, or one or the other. So another neat example here involving sine and cosine exists. I'll show you at least an example doing just exactly what you're talking about in 1 second. Any other questions on this example? Do we all see why we start with this integral? Because x squared is the upper function and x cubed is the lower function. Okay, then let's look at something a little more challenging along the lines of what Elise is asking. What if they cross the x-axis? We've seen that if functions are negative, the integral will measure the area as negative, but what about here? So let's find the area between f of x equals sine x and g of x equals cos x from x equals 0 to x equals pi. Well, that means I need to start with a sketch of these sine and cosine functions, at least from 0 to pi. For shits and giggles, let's sketch them all the way out to 2 pi. So I'll call that 2 pi. That makes halfway about here pi, which makes this pi over 2, and this 3 pi over 2. I'll start with my sine function. Let me mark off a -1 and a +1. So the sine function we know starts at the origin, goes up to 1 here, 0 here, -1 here, and back to 0 here. So here's my sine function. All right. And the cosine function, maybe I'll put him in a different color, red. He starts up here at 0, 1, is 0 at pi over 2, is -1 at pi, is 0 at 3 pi over 2, and is back to +1 by 2 pi. So he looks like this. Okay. So this is g of x equals cos x. And this fellow is f of x equals sine x. And we notice a few things. These guys do change places, right? So I'm looking for the area between these two curves from 0 to pi. That means I want this area and I want this area. Now here's the good news. You don't have to think about who's positive and who's negative. You just have to think about who's upper and who's lower. That's enough. So even though the red function starts positive and then goes negative here, it's not going to have an effect on my setup. I do need to think about splitting up the integral, though, right here, which is where sine and cosine are equal. That's pi over 4. So let me set it up kind of schematically. I'll do the integral from 0 to pi over 4 of the red function, cos x, minus the purple function, sine x. And then I'll add that to the integral from pi over 4 to pi of the upper function here, and the sine function stays above the cosine function everywhere here. So this would be sine x minus cos x, the lower function there. Does everybody see that? So in this region, red is upper, purple is lower. So I integrate from 0 to pi over 4, red minus purple. And everywhere in this region, the purple is the upper, the red is the lower. So I integrate purple minus red. So that's from pi over 4 to pi, purple minus red, or sine minus cosine. And now again, each of these antiderivatives is easy. An antiderivative for the cosine function is sine. So this is sine x minus an antiderivative for the sine function is negative cos. And that will be evaluated from 0 to pi over 4 plus antiderivatives here. An antiderivative for sine is again negative cos minus an antiderivative for cosine is positive sine. And this piece gets evaluated from pi over 4 to pi. And this plus is this plus. So Elisa, do you feel like this example kind of helps with that? In other words, if we cross the x-axis, it doesn't matter. It's always just upper minus lower, regardless of where they are with respect to the x-axis. I'm going to leave that one alone, but yeah. Okay, so moving right along, we can clean this up a little bit. This is sine x plus cos x evaluated from 0 to pi over 4. And here we can actually factor out a negative and treat this as minus cos x plus sine x evaluated from pi over 4 to pi. So if I plug in my upper bound, pi over 4 here, then I'll have the sine of pi over 4, which is root 2 over 2, plus the cos of pi over 4, which is also root 2 over 2, minus the sine of 0, which is 0, plus the cos of 0, which is 1. And from that, I'll subtract what I get over here. At the upper bound pi, the cosine of pi is negative 1, and I have to add that to the sine of pi, which is 0. And then I subtract what I get when I plug in this lower bound, which is root 2 over 2, plus root 2 over 2. And finally, I can distribute any negatives and clean things up. Here I've got root 2 over 2 plus root 2 over 2. That is 2 copies of root 2 over 2. That's just root 2 minus 1. That's this first bracket. And then from that, we're going to subtract. This piece is negative 1 minus, and this is another copy of root 2. This is root 2 over 2 plus root 2 over 2, or 2 times root 2 over 2, which is root 2. And then here, if we want to, we can clean this up a little bit more. That is root 2 minus 1 plus 1 plus root 2. Distributing all our negatives, the 1s go, and you get 2 times the square root of 2. So that is the area between sine and cosine from 0 to pi. It's 2 copies of the square root of 2. All right, any questions on this? So the fun happens on, or maybe I shouldn't say the fun, but this can get a little bit more challenging if rather than having one function always above the other, always below the other, they change places, right? These guys change places, but you always subtract upper minus lower and then integrate. If they happen to cross, then you have to do 2 integrals because sometimes one is the upper, sometimes the other one is the upper. The other thing you're going to see, and I didn't include any of this in your homework here, but you'll see it at the start of Calc 2, is the situation where rather than having y as a function of x, x is a function of y. Before we move on, let me just kind of set this up as a schematic. So the area between y equals f of x and y equals g of x from x equals a to x equals b is a few ways of writing it. Integral a to b, absolute value of f of x minus g of x dx, which is the integral from a to b of the upper minus the lower. And sometimes you'll have to split these, right? That's the idea. If they change places, you'll have to split it up. And so your bounds might not be a to b, it might be a to something in between, upper minus lower, and then that something in between to b, upper minus lower, where the upper and lower have traded places. This is the formula they give it in the textbook, but it's a little opaque. I encourage you to think about it like this. All right. I'd like to do one example where y is a function, or where x is a function of y instead of y being a function of x, just so we can say we've shown it to you. But before that, I want to look at some more complicated examples where we need to use other methods of integration. So here is what they're showing you. They build up their own Riemann sums, and you can see, yeah, it's upper minus lower, like we said. The recipe as it's given in the textbook is just the absolute value of the difference, but we'll have more fun. Yeah, here they talk about what to do, right? If they switch places, sometimes it's f minus g, sometimes it's g minus f. But the easier way to think of it is just upper minus lower. So they do the cosine and sine example, but before we jump to left and right stuff, let's look at something fun. And maybe something that requires a little bit of something clever, some substitution would be nice. Yeah. Okay. These are a little tricky. X over 1 plus x squared, the x minus 2 of the x. Let's look at number 31. All right. X over 1 plus x squared, I know what that looks like. X squared over 1 plus x cubed, I'm not sure. Let's take a look at Desmos, see what Desmos tells us about these. So this is called a witch. It's a special kind of curve. This one we know. The other one, though, what was it? X cubed? X squared over 1 plus x cubed. This guy I don't know so well. He's a weird curve. I wouldn't expect you guys to know what he looks like either. But we can see it here. And they want us to find the area between them. Sketch the region enclosed by the given curves, find its area. So the only place where there is an area enclosed by these curves is here, from 0 to 1. So let's do it. I'm going to write down the problem, then I'll switch back to the .cam. Okay. One last look at what that weird one looks like. Yeah, okay, he blows up at -1, then hooks back around there. Okay. So I want to sketch the region bounded between x over 1 plus x squared and x squared over 1 plus x cubed and find the area x over 1 plus x squared, I know looks like this. And he'll flatten out that way too. I just care about this stuff. 1 over x squared over 1 plus x cubed looks a little weirder. He's kind of concave up in here, so he's going to blow up to infinity as we go that way. He's concave up in here and then does something like this. So this is g of x, this is f of x. And this place where they meet, you would have to find that. So you have to find the intersection. That's where f of x is equal to g of x. And I expect from the graph that I saw in Desmos that there will be two such places, 0 and 1, but to verify that, we would set up this equation and look for solutions. Now, 0 is clearly a solution, 1 is clearly a solution, because if you plug those in, you get 0 equals 0, and 1/2 equals 1/2. But if we had to discover this, you could cross multiply, and you get x times 1 plus x cubed equals x squared times 1 plus x squared. And this is the same as x to the 4 plus x equals x to the 4 plus x squared. And then you can pull everything to one side. So what do you get? Subtract x to the 4 from both sides, and you can subtract x from both sides. You get 0 equals, what do we get? X to the 4, those cancel. And then x squared minus x, which is the same as saying x times x minus 1. So yeah, this has two solutions, x equals 0, or x equals 1. So this is indeed 1, and this is 0, and the area I'm looking for is this. Now my upper function, everywhere between 0 and 1, is f of x. That's the x over 1 plus x squared. And my lower function between 0 and 1 is g of x. That's x squared over 1 plus x cubed. So my area, the area I'm looking for is the integral from 0 to 1 of the upper minus the lower, which is x over 1 plus x squared minus x squared over 1 plus x cubed dx. So that's the integral that I need to solve. Again, f of x, this guy is x over 1 plus x squared, and g of x is x squared over 1 plus x cubed. This is a case where I would want to split the integral up. So I would handle this as the integral from 0 to 1 of x over 1 plus x squared dx minus the integral from 0 to 1 x squared over 1 plus x cubed dx. There might be other ways to do this, but this is what comes to mind for me because I know how to handle this guy and I know how to handle this guy. Who can help me with the first integral here? if it was just 1 over 1 plus x squared, that would be an inverse tangent, but it's that x upstairs is actually making this something else. So it's arctan is a good guess, but remember the derivative of arctan x is 1 over 1 plus x squared. So that wouldn't account for this x, and this x is not a constant, so I can't pop it out or anything. So it's a good thought, but it's not actually gonna work quite like that. Any other ideas how we could handle this integral? We're just going to focus on this guy for now. Think about the section that we just talked through, the section that we were working on last week. Very good. Yeah, Matthew's got it. And Andrew. Good, good, good. We're going to sub for the bottom. I'm sure there's a joke in there somewhere, but the move here is to substitute u equals 1 plus x squared. It's true then that du is 2x dx, and since this is a definite integral, you also absolutely must change your bounds. When x is equal to 0, u will be equal to 1 plus 0 squared, so u will be equal to 1. When x is equal to 1, u is equal to 1 plus 1 squared, which is 2. Also, this x dx, so I'll go one more step here. I'll rewrite this as integral 0 to 1, 1 over 1 plus x squared times x dx. Because x dx is 1/2 du. All right, so this is the piece I have to help me with my differential. I have, though, that du is 2x dx. So if I divide both sides by 2, I get 1/2 du is x dx. So now I'm ready to rewrite this in terms of my new variable. The 1 over 1 plus x squared is 1 over u. The x dx is 1/2 du. And my new bounds are 1 to 2 instead of 0 to 1. So I can pop out the 1/2. I've got integral 1 to 2, 1 over u du. Is everybody with me so far? Does everybody see why this is this? I did find for you guys, by the way, that article. Let me show you really quickly. That I mentioned in class about why we need the differentials, why substitution works, and why we change the bounds. So this is a really good page. Check it out in the announcements. It explains why you need to change your bounds and what's going on with the differential. So if you wanted to find the area from 0 to 1/2 under the red, that's the same as the area from 1 to 1.5 under the blue. Yeah, the shapes here are the same. So if you were making a substitution that changed one of these into the other, you would need to change the bounds from 0 to 0.5 to get this area, to 1 to 1.5 to get that same area. So you got to change your bounds, because when you make a substitution, you're changing your coordinate system. The other thing here is that when you make a substitution, you're really scaling the axes. The axes change. So not only do you need to change the bounds, but also the differential can change a sort of density, a sort of how much each little piece is weighing. So please check out this example here. It's a really, really good example. They show changing the bounds. They show what the differential does. And they ask you to think a little bit about this concept of density, which is a subtle concept. We change the bounds because the area underneath this function from 0 to 1, these are x values. This is from x equals 0 to x equals 1. When we change the variable from x to u, like we're doing here, I need to know what values of u correspond to those original values of x. So I want the area under this function from x equals 0 to x equals 1. It turns out that's going to be the same as the area under this function from u equals 1 to u equals 2. So anytime you make a substitution in a definite integral, an integral with bounds, you need to change the bounds. And the trick is not hard. You look at this substitution right here, u equals 1 plus x squared, and you plug the old bounds in. When x is equal to 0, u would be 1 plus 0 squared. Well, that's 1. So when x is equal to 0, u is equal to 1. That's my new lower bound. And to figure out my new upper bound, I plug in my old upper bound here. So when x is equal to 1, u is 1 plus 1 squared. 1 squared is 1, so that's 1 plus 1 is 2. So when x is equal to 1, u is equal to 2. So my old bounds go 0 to 1. My new bounds, which are bounds for u, are u equals 1 to u equals 2. And now we're free to do the integral. An antiderivative for 1 over u is natural log absolute value of u. And I evaluate that between my new bounds. There's no need to ever go back to the old variable because we're doing a definite integral. So finally here, this would be 1/2 times the natural log absolute value of 2 minus natural log absolute value of 1. The natural log of the absolute value of 1 is 0. Absolute value of 1 is 1. So this piece is 0. So I get 1/2 natural log of 2 because the absolute value of 2 is 2. So that's the first guy. From this, we need to subtract the other guy, right? I still have to do this integral. So also, the integral from 0 to 1 of x squared over 1 plus x cubed dx, we need to compute this. And then we're going to subtract them. So who can help me with this integral? It's a similar attack. Ellen, are you comfy with the bounds change there? I'm glad you're asking. It's a good thing you're asking. This is something I often have to yell at Calc 2 students to get them to do, and still they struggle. So I want to spend a minute making sure we're really comfy. Are you guys comfy with why we changed the bounds and how we changed the bounds? Good, Akash. That's the correct substitution for the next one. Okay, so let's go ahead and do it. Here I'll use a different letter. I'll use the variable z. The substitution suggested in chat is correct. I'll sub for 1 plus x cubed, because then dz is going to be 3x squared dx. I can rewrite this integral as integral 0 to 1 over 1 plus x cubed times x squared dx. This x squared dx isn't exactly dz. It's going to be 1/3 of dz. Also, I'll change my bounds when x is 0. The z is 1 plus 0 cubed, which is 1. When x is 1, z is 1 plus the cube of 1, which is 2. And this piece is going to be 1/3 dz, because 1/3 dz is x squared dx. Right. So Alan asked in chat, just to clarify, we only need to change the bounds when we're working with a definite integral and doing substitution. That's correct. Only if you're working with a definite integral do you have bounds to change. And then the only time you need to worry about changing those bounds is if you're making a substitution. But those are very, very common things. So definite integrals, we bump into them all the time. And probably the most common attack is a substitution. So yes, if you're doing any definite integral with any sort of substitution, that requires changing bounds. Not a problem. So from here, this piece I can replace by 1/3 dz. This will be 1 over z, and the integral will now go from 1 to 2. I can pop the 1/3 out, and I'm left with integral 1/3 integral 1 to 2 1 over z dz, which is 1/3 times the natural log absolute value z evaluated from 1 to 2, which is 1/3 natural log 2 minus natural log 1. And again, the natural log of 1 is 0. So here I just get 1/3 ln 2. Therefore, these 3 dots arranged in a triangle like this mean therefore, the area I want was the difference of those integrals, integral 0 to 1 x over 1 plus x squared dx minus integral 0 to 1 x squared over 1 plus x cubed dx. The first one we found to be 1/2 ln 2. The second one we found to be 1/3 ln 2. So we get 1/2 minus 1/3 ln 2, which is 1/6 ln 2. And that's areas between curves. It's not hard. It's not hard. It's exactly as hard as the integrals it reduces to. And those integrals, for now, will always be things that you guys know how to solve. I would never feed you a problem like this where you didn't know how to solve the integral. But if you go writing down random problems, just trying to guess at things or just trying to say, hey, for fun, let's see if I can find the area between these two, you can easily run into an integral you don't know how to solve, because integration in general is much, much harder than differentiation. So slowly, over the first few weeks of Calc 2, you're going to learn how to integrate more and more and more stuff. Right now, your goal, your task, is to get real fucking good at substitution. Substitution is harder than it seems at first. There are many easy substitution problems. There are also a lot of very subtle, very challenging substitution problems. And I want you guys to slowly be wading into those waters. So if you bump into a problem in the homework that's hard, you're having a difficult time seeing the substitution, or you just get it wrong a couple of times, rather than getting very, very frustrated, just move to another problem that seems easier and work a few of those, and then come back to that hard problem. Maybe in the interim, send me a message saying, I'm working on this, I'm having a hard time, can you help me out? And I'll be happy to kind of give you a hint. Try this substitution, or did you calculate that differential correctly? The most common mistakes, again, are not dealing with the differentials appropriately. So every time you make a substitution, the very first thing you should do, just like you see me doing, very first thing you should do is take the differential. Before you go trying to plug anything into your integral, take the differential and see if you can make it work. See if you can find this piece floating around in your integrand somewhere. You might not get exactly this, but here I had an x squared that I could group with the dx. I needed a 3x squared. Oh, that's okay. I'll just divide the 3 over. And then remember, before you do anything antiderivative wise, you need to make sure that your integral is all in terms of the new variable. No old variables floating around anywhere. All right, deep breath. You just finished Calc 1. That's all of Calc 1. Reviewing Wednesday, good question. So there are a few little topics that we have not been able to talk about that I want to talk about. I want to strike a balance between me adding in these kind of extra topics that aren't core to your skill building but are important to your comprehension, and also reviewing an appropriate amount. So yeah, Wednesday we will review. Let me use the last few minutes of class here to show you something cool. This is something I waited until the end of class because it can be seen from two perspectives, and I would like to help you see it from both perspectives. It's called the mean value theorem. It was proved by Cauchy. At least Cauchy proved the big boy version of it that I am most familiar with. But it may have been discovered before then. It's entirely possible that Newton, for example, was aware of this, but I want to show you something neat now. This is called MVT, or the mean value theorem. The word mean can mean a few different things in the English language. Of course, it can mean cruel or unkind, but the sense in which we're using the word mean here is average. The mean value theorem, from the perspective of the derivative, says the following. If f of x is continuous on the closed bounded interval AB and differentiable on the open interval AB, then for some number C between A and B, we have the following. The derivative of f evaluated at C is equal to f of b minus f of a all over b minus a. This is one way of stating the mean value theorem. I'll call it MVT1. And the picture is this. Maybe over here is A, and maybe over here is B. The function I've just drawn is certainly differentiable and continuous everywhere on the interval AB. And the object on the right-hand side over here, this fella, is the slope of the secant line. Remember when we talked about secant lines at the very beginning of the class? It's the slope of the line connecting the point on the left with the point on the right. It's the slope of this dotted line. What the mean value theorem says is that somewhere in between A and B, there is a tangent line, f prime, whose slope is the same as the slope of this secant line. So let me go hunting around in here. I think I can find one right about here, where if I look at the tangent, it's parallel to that secant. I think there's another one right about here, where if I look at the tangent, it's parallel to that secant. Isn't that neat? So what this says is, you give me a tangent line, I can find you at least one place where the tangent is parallel to that secant. So this first guy, I'll call him like C1, and this other guy, I'll call him C2. So what you see is that the red tangent lines are parallel to the blue secant line. And no matter how you connect this point to this point, there will be at least one such place. There's another way to say this. And I want to get the phrasing exactly right, so I'm going to look it up here in your book. Mean value theorem for integrals. Yeah, okay. So this says if f is continuous on AB, then there's a number c in AB such that f of c is the integral. All right, I got you. No differentiable. And there is a number c between A and B such that f of c is equal to 1 over b minus a times the integral from a to b f of x dx. Now the secant line, the slope of the secant line, come back here for a second, is the average rate of change for the function from a to b. This guy has a special name. He's called the average value, or sometimes denoted f bar, is the average value of f from a to b. And what the mean value theorem for integrals, this second formulation of the mean value theorem, what it says is that if you look at your function f from a to b, think about all the area here. There is a unique constant function such that the area enclosed by this guy, all of the purple area here, is the same as the area enclosed by a certain rectangle. I'm going to take a guess and say that that's something like this. So this would be f av. And the area in the red rectangle is the same as the purple area. And what the mean value theorem for integrals says is that this guy intersects or crosses the original guy, so that f of c, this y value right here, the point on the graph there is c comma f of c. So the f av is actually equal to one of the function values. These are two different ways of actually saying the same thing. And I would like you guys to keep these pictures in your head. From the perspective of a mathematician, or the perspective of someone who's trying to really understand calculus in a deep way, these two pictures are very important. These two theorems, two characterizations of the mean value theorem, are hugely important for proving other theorems and for figuring things out at a sort of high level about functions and rates of change, calculus, areas, averages. If you're into statistics and you've ever studied continuous random variables, this sort of thing is very, very important. If you're into physics at all and you like to talk about speeds, trajectories, average rates of change, average velocities compared to instantaneous velocities, this picture is very important. One of my favorite little anecdotes, and I'll end class here today, is that if, suppose there's 100 miles between here and Orlando, it's roughly true. And a cop sees me leaving Gainesville at 12 p.m. Another cop sees me arrive at Orlando at 1 p.m. and they radio to each other and let each other know that. You know, cop says, hey, I saw John leaving Gainesville at 12, and the other cop gets that message. He's like, hey, I just saw John arrive in Orlando and it's 1. There's 100 miles between Gainesville and Orlando. Well, that means that John's average speed between Gainesville and Orlando must have been 100 miles an hour. Sure as shit, they never saw me go 100 miles an hour. The cop in Gainesville just saw me leaving my house. I was going maybe 20 miles an hour. And the cop in Orlando saw me arriving wherever I was arriving. I was probably going about 20 miles an hour there too. Even though they never saw me going fast, they know that somewhere along the way, my instantaneous rate of change, the red tangent line, has to have been the same as my average rate of change, the dashed blue secant line. So the cop in Orlando could go ahead and issue me a ticket for going 100 miles an hour. Because if my average speed was 100 miles an hour, then at some point I must have gone exactly 100 miles an hour. Slower sometimes, faster other times, but at some point, if my average speed was 100 miles an hour, then my instantaneous rate of change, my actual velocity must have, at least at one point, maybe more than one, have been exactly 100 miles an hour. So 2 different characterizations of what's called the mean value theorem, both very, very important, although neither make for great skill building problems. I mean, I could ask you to find the value of C such that this is true, or find the value of C such that this is true. Those are boring. What's important here is the picture and the concepts. So I encourage you to read about the mean value theorem in the textbook, and make sure you remember the 2 statements of the theorems here. They're both beautiful and neat things. That said, I'm not going to test you on them. Or I may give you a very gentle concept, like true-false question about them, but I'm not going to do any high-level computation, or sorry, low-level computation here. So the things I want you guys working on: become badasses with substitution. All right, get to a place where substitution is something that's like bread and butter for you. Real simple, makes good sense. There's no uncertainty. If you're having any problems with the homework, please contact me for help, because exam 3 and the final will both have plenty of substitution problems on them. The last bit of material that is on any of the tests in this class is section 6.1, areas between curves. And that I will keep just to the final. I won't put any area between curve stuff on exam 3 because you won't have had time to practice it. But the final will absolutely have areas between curves. And then the exam 3 is just going to go up through section 5.5 on substitution. That is all I have planned for you guys today. Are there any questions for me before I let you go?
When is exam 3?
This Friday.
And I don't understand the significance of the bottom graph for the section 2 of MVT.
So this is saying that compare the 2 areas, the purple area and the red area. The red area and the purple area are the same, right? The area in this red rectangle is the same as the area under the purple graph here. And the neat thing is that the height of this red rectangle is determined by one of the heights along the purple graph. It's not possible that this red rectangle is above the whole thing or below the whole thing. Somewhere this constant function is equal to the value of the purple function. In other words, this number, right? The integral from a to b of f of x is a number. Divide by b minus a, that's still just a number. This number, which we call the average value of the function, is actually equal to the output for the function at some particular value of c. So another way of thinking about this is if you have a continuous random variable where the probability of selecting one of these, think of it like as a histogram, probability of selecting something over here would be higher, probability of selecting something over here would be lower. Whatever the mean of that distribution is actually attained. The mean is actually a part of the set being averaged. That's one way to say it. There's a million different ways to characterize this. The way the book discusses it, they say the geometric interpretation is that for positive functions, there is a number c such that the rectangle with base AB and height f of c is the same area as the region under the graph from A to B. So the dark shaded rectangle here is like our red rectangle. The dark shaded rectangle has the same area as the area under the blue function. And the coolest thing about this is that the height of the dark shaded rectangle is actually determined by the value of the blue graph at some C in between A and B. That's all. I know it sounds like it's not too consequential, but depending on how you choose to interpret it, it can be quite consequential. Can tell us some interesting things about distributions of random variables. I'm sure there's a connection here to physics. I just have to think about it a little bit. Like, yeah, here you go. If this is your velocity function, the blue is how fast you're going at any given moment, then you know the blue area is the total distance traveled. The gray rectangle then, being the same area, means if you walked at this constant speed, whatever the height of the red constant is here, you would cover the same amount of distance as if you start off running really fast and then slow down and go really slow and then speed up a little bit. So the red velocity here, this y value, that is this constant function, is the constant speed you would have to walk to cover the same distance as someone who goes really, really fast, then slows down and then speeds back up. So again, there's this concept of like average, right? The mean value theorem is a theorem about averages. That's how I would interpret it. I would say the average value of the function is a constant, and that constant is actually coming from an output of the original function itself. Or every function at some point attains its average. Maybe the function is outputting really big numbers and then outputting really small numbers and then outputting really big numbers. One of the numbers that it output was actually its average, as long as the function is continuous. Does that help?
Yeah, thank you.
Okay, cool. I hope it does. I know this stuff is complicated. And again, I just want you to think about this on a concept level. If you want to dive in a little bit deeper, section 6.5 here is actually pretty good. They talk about how you can define an average for a finite set, add up all the things, then divide by the number of numbers. They extrapolate to a Riemann sum and give you this integral. That's why we call it the average value. But read as much or as little as you like. I'm not going to push you too hard on the mean value theorem. Do, however, make sure that you become a rock star at integration by substitution. If you want to talk any more about this stuff, you can come see me in office hours, send me a message on Canvas. But that is it. I will see you guys next time. Wednesday again, we'll review for exam 3. We can do whatever you guys like. I may toss in 1 or 2 other little discussions like this, but please come with problems you want to work on in class Wednesday. Most of the day will be review for you. All right, take care, guys. Have a lovely afternoon. And if you'd like to talk to me or meet up, just let me know.